Swayam Prabha. Digital India. Educated India.
Okay, we get started. I am going to discuss ideal solutions. Actually, one topic I left out is equations of state. I will discuss that a couple of classes down the line, because we have gone on to liquid mixtures. I will also discuss ideal gaseous mixtures. I will do equations of state later. In the case of ideal gaseous mixtures, there is one redeeming feature that helps you solve the Gibbs-Duhem equation using experimental data. The way this happens is you have delta mu I by delta P is equal to Vi bar. This is an exact expression. In the case of ideal mixtures, ideal gaseous mixtures, first of all, for ideal, this is ideal mixing. If the process of mixing is ideal, there is no volume change on mixing, because ideally molecules do not occupy volume. So, there is no change in volume, and ideally molecules do not interact with one another, so there is no enthalpy change. So, these are the two basic definitions of ideal mixing. If that is true, this is then if it is an ideal gas, that is if the pressure is sufficiently low, Vi is simply RT by P. So, you get mu I is equal to, if you integrate this is done at constant pressure and composition, temperature and composition. So, you will get some function of temperature and composition plus RT ln P. In particular, you have mu I pure is some function of temperature plus RT ln P. To find this function of composition, you separate out mu I and RT ln P. You have f of t and xi, you know you have to solve the Gibbs-Duhem equation. Now let us put down the, I will come back to this in a minute, but let me put down the Gibbs-Duhem equation. We have already seen that this is simply xi partial of mu I with respect to xj. We said the simplest solution is mu I varying as log xi. I write varying as because one left side is energy per mole, the right hand side is dimensionless. So, you have to do some corrections. So, I can define this time an ideal solution. I will show you that I can also come from another route from the gaseous behavior and come back to the same conclusion. First of all, define an ideal solution by writing mu I ideal is equal to mu I. If you, okay, I will just write, or I will write this as function of t. In fact, I will make it this function of t comma p. This is the definition of an ideal solution. Now clearly as xi goes to 1, f should go to mu I. This ideal refers only to the mixture, only to this mixing process. So in the limit as xi goes to 1, you do not have mixing, left hand side will become mu I pure. So f of t has to be equal to mu I pure, whatever the value of the chemical potential at that temperature and pressure is. So I have mu I ideal this will give you all the results that you need to define an ideal solution, because mu I ideal by P, this side is simply Vi bar ideal, on the right hand side I simply get Vi. Then Hi bar ideal by T squared, or minus of this, is partial of mu I ideal by T with respect to T. This is rigorous thermodynamics, but if I do the right hand side, this comes from the right hand side. On the right hand side, if I divide by T and differentiate with respect to T at constant pressure and composition, I simply get delta mu I pure with respect to T, mu I pure by T with respect to T, which is minus Hi by T squared. So you get Hi bar is equal to Hi, Vi bar is equal to Vi, which is the definition of ideal mixing. Ideal mixing says mixing without change in volume and without change in energy, enthalpy. I can go further because of this. If I have an ideal gas, then I have mu I is equal to this plus RT ln P, for a pure substance. Again this, let me put this in here. So if I have mu I ideal for an ideal gas mixture, for a mixture of ideal gases, I have to write two lines there, two words there, for an ideal mixture of ideal gases. The ideal mixing process can be in the liquid phase, can be in the gas phase, but I am taking the special case of ideal mixture of ideal gases. For mu I pure, for an ideal gas, I got this result. All of this is for ideal gas, right, because I have substituted ideal gas here. Ideal mix of ideal gases. So I get mu I ideal is equal to some function of T plus RT ln Pxi. You have to give an interpretation for f of t, simply to say what it represents. When xi goes to 1 and p goes to 1, this term goes to 0. When xi goes to 1, you get pure substance, pure I. So pure I at p is equal to 1, at p is equal to 1 is sufficiently low pressure. We usually measure p in bars, So if you use those units, then when P is equal to 1 bar, you get f of t is simply mu I, the chemical potential of pure I at the temperature of the mixture at pressure equal to unity. So we write this as mu I is equal to mu I, this is mu I ideal, mu I 0 of t plus RT ln Pxi. Also from this equation, let me give these equations numbers. This is 1 and Vi bar equal to Vi is for ideal mixing, and this is for ideal gas, this is 3. So this will be 4, this will be 5. This is of course one number every day, 6, 7, then 8. This simply proves that this is, hence 8 satisfies conditions of ideal mixing. Conditions of ideal mixing are simply delta V mix is equal to 0, delta H mix is equal to 0. And then finally this here 8, let us say this is 9. First of all, from equations 1 to 3, I have delta mu I actual minus mu I ideal by delta P this, when I write ideal here, it only means ideal mixing on mu I. Okay, where I have detailed mixing of ideal gases, I will write it explicitly, but normally when I write mu I ideal, I only mean ideal mixing. That is, the gases need not be individually ideal, but I am assuming the process of mixing is ideal. This can happen at very high pressures between say ethane methane mixtures. Similar substances will mix without change in volume, without change in. So if I take this difference, this is Vi bar, the first one, if I differentiate this I get Vi. Now mu I minus mu I ideal is therefore equal to, I am integrating from 0 to P of Vi bar minus Vi dP plus some constant. Now I can determine the constant very simply in the case of gas phase, because in the limit as P goes to 0 all gases behave ideally, therefore this mu I also becomes a mixing of ideal gases, therefore I have mu I minus mu I ideal is 0 at P is equal to 0, so the constant is 0. This is because this is 0, I will write here, since all gases behave ideally, as P goes to 0. I have this integral 0 to P of Vi bar minus Vi dP. I write this as integral 0 to P or minus, I am adding and subtracting RT by P inside the integral and splitting the integral into two parts. This is defined as, this is 3 lines, is just a definition. Write this as RT ln of phi minus RT ln of phi pure. When Vi bar is replaced by small vi, this becomes the specific volume of the pure substance. So, I recognize this by writing phi pure. Incidentally, Smith and Vaness has a slightly different notation. For phi he writes phi cap, for this he writes phi. So, when he writes phi he is talking about pure fugacity. The mixture value fugacity coefficient, this is called fugacity coefficient, I will come back to it in a minute. Phi is called, phi cap is the value in the mixture. I am too used to this notation to change. If I change halfway through I will make a mistake again. I will stick to this notation. So, phi for us is phi cap, our notation Smith and Vaness, and our notation is phi pure and this is phi. Similarly, mu I cap in Smith and Vaness is chemical potential in the mixture, and mu I is the chemical potential of pure I for him. The reason we give these symbols is because you need default options in chemical engineering. You can put phi equal to 1 as an approximation, whereas you would not know what the default option for chemical potential was. So, we have not really done any significant, at this stage we have not made progress in terms of defining the composition dependence of the chemical potential, but we have expressed it in terms of a quantity. For example, in the gas phase this is completely measurable, Vi bar is measurable. So, if I know the composition dependence of the chemical potential, if I know the composition dependence of this molar partial molar volume, that is all I am saying. So, if I know one I can get the other. I can't make this connection in the liquid phase because liquids do not have an asymptotic behavior either at a limit of temperature or at a limit of pressure. Because all gases behave ideally at P is equal to 0, this integration constant vanished for you. You will not have such a facility in the liquid phase. So, in the liquid phase you are stuck with solving this equation directly. Here if you have experimental data on Vi bar, you have a solution of the Gibbs-Duhem equation, because the Gibbs-Duhem equation simply tells you then that mu I minus mu I ideal is this and mu I ideal is given by this. So, you got your whole this thing worked out. So, let me get back and write these equations. Mu I pure in particular, okay, let me write this out. Mu I pure is equal to mu I 0, I am sorry, this is mu I 0. I can just simply write mu I 0 because mu I 0 that the notation I have used there is the chemical potential of pure I at the temperature in question and pressure equal to 1, plus this should have been an ideal case times Vi pure. Because if I did the same thing for mu I for the pure case, mu I pure minus mu I ideal pure would have been simply Vi minus RT by P. Maybe I should write it here. See, it follows that mu I pure minus mu I ideal simply equal to 0 to P. Because it is pure, Vi bar becomes simply Vi. The second case, because it is ideal, it becomes Vi minus RT dP. This is mu I ideal pure. ideal pure we had already, that is mu I 0, you would have mu I ideal pure would have been mu I 0 plus RTL and P xi or RTL and P. If I multiply by, oh there is no xi here, P phi I pure, mu I 0 plus RTL and P would be the value for mu I pure ideal. I add on a correction for non-ideality which is phi I pure. Then I have mu I in the actual mixture is equal to mu I ideal mixture plus RTLN Pxi into phi I. I have actually mu I is equal to mu I 0, mu I ideal mixture is already there, Pxi is there, so this is mu I 0, sorry. I have to come back, I will write the different equation. These are the unique models for the gas phase. Phi I is given in terms of Vi bar minus RT by P dP, and phi I pure is simply Vi minus RT by P dP. For gases, this completes the description. Remember that the Gibbs-Duhem equation is written for a homogeneous phase. When you write dG is equal to minus STT plus VdP, you are writing for a homogeneous phase. So you have to solve this, since luckily we have only 3 phases of aggregation. You have to solve it for the solid state, the gas state and the liquid state separately. So I have done the gas phase, now we will do the liquid phase, liquid mixtures. For liquid mixtures, first no asymptotic behavior. If you are able to find an asymptotic behavior, you are in for a Nobel Prize again. But some of these things are not worth searching. When the liquid range has been covered, people have looked everywhere. So you have to need to solve Gibbs-Duhem equation. What we do is, the simplest solution is mu I ideal again. I still have possible simplest solution is however, you must notice that in liquids you have all kinds of mixtures. I can have gas dissolved in liquid. So suppose I referred to carbon dioxide in water and I referred to carbon dioxide, then as if you go to the temperature of the solution, if you go to the temperature and pressure of the solution, go to the pure state is a gaseous state. It is not realizable in practice. That is, I cannot take a mixture of composition Xi, where Xi represents the composition of carbon dioxide, mole fraction of carbon dioxide in the mixture, and take that mole fraction continuously to 1 without change of phase. And the Gibbs-Duhem equation is written for a single phase, so I have to solve within that phase. So what we do is write this as simplest solution for, we give name for mixtures, we classify mixtures into solvent mixtures and solvent solute mixtures. So this is valid only for solvent mixtures. In solvent mixtures, you can take the mole fraction of all the components individually to unity without change of phase. That is the definition of a solvent mixture. For every component I can go to mole fraction unity and still preserve the liquid state. So this is the simplest solution, this is a solution. So what you do in practice is write for non-ideal solutions, or real solutions as they, you have mu I is equal to mu I pure at Tp, again for solvent mixtures only. I will treat the other case separately. I write mu I is equal to that, where I have to tell you what gamma I is. In this case, when xi goes to 1, left hand side becomes equal to this, so gamma I is 1 in the pure state. So you write along with this, you notice that gamma I goes to 1 as xi goes to 1. This quantity gamma I into xi is called Ai, it's been called activity. It was a term coined by Lewis long ago. Incidentally, Lewis is credited with being the first expositor of classical thermodynamics, because Gibbs needed an interpreter. What Gibbs said was absolutely right, but very terse. Gibbs would say in the footnote, obviously, and he will say in the footnote, if necessary this can be derived, and so on. Then Lewis will do the derivation. So Lewis's book had all the, it was like he took notes from the master and filled them up. So in ideal solutions, the role of non-ideal solutions, the role of mole fraction is played by Ai, the activity. And the activity, the default option in all chemical engineering design programs is to set gamma I equal to 1. But you can go terribly wrong. There are mixtures in which gamma I can be 1500, which means xi being a representative of mu I is meaningless. Log xi does not any longer represent. But those are exceptions. But typical gamma values of 2, 1.5, 2, 3, etc. are very, very common. Many mixtures. So we will do lots of examples in which these, and that will make a lot of difference. As I told you, finally you are going to use delta G is the work done. Delta G is xi mu I minus xi mu I for the mu I pure. So that is the change when you do mixing or unmixing. You take air, separate it into oxygen and nitrogen, you can calculate how much work is done in the process. I will do that calculation. When you do the difference, essentially this RTLN gamma log gamma I xi represents the work in bringing, you will show that it is equal to the work in bringing 1 mole of I into a mixture of J, say if you have a binary system. And since the work depends on log of xi, if it is log gamma I xi and gamma I turns out to be 2, you will make a mistake of RTLN 2. It can be a large difference, that is all. So this is your activity coefficient. Now you have not really done anything, you only change words, because if I substitute this into the Gibbs-Duhem equation, now let me go back to the Gibbs-Duhem equation, it will plague you till you solve it in some way or other. Now substitute this quantity, give these, finished 9 I think last, we will call this 10, this can be 11, 12. So substitute 12 into the Gibbs-Duhem equation, do this by inspection. Mu I pure is not function of xj at all, so all of it will cancel. RTLN xi satisfies the Gibbs-Duhem equation. So when I do sum over I of xi partial of log xi with respect to xj, you know we get 0, right. For I equal to j, you will get 1, for the last component r you will get minus 1, so you will get 0. So only thing that remains is log gamma I, and RT is a constant. So this will give you sum over I partial of log gamma I with respect to xj is equal to 0. To solve this, you go back to the other formalism. You remember we wanted to look at delta G, you model delta G and you get all your equations for mu I. Instead of mu I, now you will get log gamma I. So the equations are very simple. You get Gxs by RT. I will write this for a binary. X1 now log gamma 1 plus x2 log gamma 2. The reason is Gxs is delta G minus delta G ideal. Delta G is G after mixing minus G before mixing. Minus G after mixing ideal minus G before mixing. Gxs by definition is delta G minus delta G ideal. So this is G after mixing minus G after mixing ideal. G after mixing is sum over xi mu I, these two will cancel. Before mixing, these two will cancel. I am looking at the ideal mixing process now. Xi mu I minus mu I ideal. So mu I ideal is mu I pure plus RT ln xi, mu I non ideal is mu I pure plus RT ln gamma I xi. So the only difference is log gamma I. So this is equal to RT sum over I So Gxs for a binary, this in particular will give you x1 log gamma 1 plus x2 log gamma 2. Okay, so I suppose I should say here since this is okay. So then I do the same thing that I did before, which I differentiate this partial of delta Gxs by RT by delta x1 is log gamma 1 minus log gamma 2 plus and this term is 0 because of the Gibbs-Duhem equation. I just have to solve these two equations algebraically. Equation 12, this is 13, this is 14. And if you recall, when we did one Laur's equation, we really got an expression for Gxs, not for delta G. The models for solid mixtures are identical. We do not often use them in chemical engineering, we use them in metallurgical engineering, because basically between solids and liquids there is not really much difference. They both represent the condensed phase. Molecules reasonably closely packed, and the density of the solid is not very different from that of the liquid. You have a very well defined crystal structure in solids. In amorphous solids you do not have a crystal structure, but you have a well defined, reasonably well defined structure. In the case of liquids you have a little more entropy. So the models for solid mixtures are similar, but we do not use them often in chemical engineering, as I told you. Main solid mixture problems are in metallurgical thermodynamics. So primarily we will deal with liquid mixtures, we will of course deal with gaseous mixtures, but most of the time your gaseous mixtures will behave themselves. I mean, you will have to calculate Figastic coefficients, but you will know the equation of state and you can calculate it that way. For this you will have to go through, for liquid mixtures I will write the model for Gxs. And the corresponding log gamma 1. you can get this from tables. This is, you will have to write this separately for two classes of mixtures. I will deal with solvent solute mixtures later. For solvent solute mixtures, the model for the solvent will remain the same, but for the solute I will have to write it differently. Gxs can be 0, this is ideal solution gamma 1 equal to 1, or I will just write gamma 1, it is okay, log gamma 1 or Gxs can be A x1 x2 Gxs by RT, this is called this is ideal, we will give a name for the model. This is called Porter's equation. And if you do that solution that I have given in 14, you take this expression, differentiate it and so on, you get A x2 squared for log gamma 1. If you like for log gamma 1 here, you will get 0. Gamma 1 is 1, log gamma 1 is 0. So you can build models of this kind. I mean, you get A x1 x2 into 1 plus B x1. You can write higher polynomial models. This is Margules. It's called 2 suffix model. It's as I told you, you can write this as A12 and this as B12, so it is called 2 suffix. I think he even writes this as A12 and A21 or something, it does not matter, 2 parameters exist and you have to solve that. I do not remember the solution, but you can solve those equations simultaneously and get the values. What I will do is put up a table of this. Incidentally, there is a very nice, I personally do not like the book much, but it is well written and it is written by an industrial practitioner. So it is written typically with a lot of redundancy. It has got everything worked out. For an open book examination it is ideal, because if I tell you the model, you do not have to start solving those equations in the exam and make mistakes in solving simultaneous equations, because I will never find out whether you know your thermo, you will make a silly mistake there. So the best thing is for you to keep these things. Wallace has a table, I will try and put that table on the web itself. He has this model and he has this solution for log gamma 1, log gamma 2, he has got it for ternary mixtures, for any number of multi-component mixtures, and in case you do not know how to simplify the multi-component mixture equation for a binary, he will separately give you binary tables also. So he has got all that. It is called, I think, chemical phase equilibrium. I think it is just called phase equilibrium, I do not remember exactly, but Wallace is a practicing engineer for 15-20 years. Okay, so as I said, once you have models for the chemical potential, the various models in you will also have to go through the model for Van Laar, which is an expression for RT by Gxs. The only thing you have to be careful about is that Gxs has to go to 0 in the limits, otherwise you can propose your own model. I mean, but if you have a phase equilibrium, if you have vapor liquid equilibrium, then you will get mu I liquid is equal to mu I vapor. This you have already shown. Now the whole purpose of all this exercise was to express mu I liquid in terms of measurable quantities, and we have shown that everything is measurable except the composition dependence of the chemical potential. So this alone you have to do modeling. So with the model you get it in terms of composition again. So what you do is, when you solve this phase equilibrium problem for mu I liquid, I have to go through a little more. So here you express in terms of T, P and composition and you will get one term here that represents and mu I liquid pure, because your model is mu I is equal to mu I pure plus RT ln gamma I xi. When you write it for the liquid phase, this is mu I liquid pure. This will come out similarly in terms of mu, this will come out in terms of mu I 0 always, will come out in terms of T. What we will do hereafter for composition in the gas phase, we will use Y, for liquid phase we use X, that seems to be a convention, composition Xi. So the only thing that still gives you a little difficulty is this mu I 0 that appears in the gas phase equations and the mu I liquid pure that appears in the liquid phase equations. So you have to relate mu I liquid to mu I vapor. I will do that and then I will go back and do solutes in solute solvent mixtures. If you go back to your pure component phase diagram, P versus H, this is T is equal to Tc. So you have liquid plus vapor diagram here. So if you are talking of liquid pure, you are talking of substance below the critical point, it has to be, that is the way the critical point is defined. So the way you connect the two is to recognize that at this point the chemical potential of the liquid is the same as the liquid chemical potential of the vapor. So if I want to cancel this mu I 0, I have to express mu I liquid in terms of mu I gas. If I do that, then mu I gas will have the mu I 0 in it, which will cancel on both sides. So having introduced a mu I 0, which is a hypothetical quantity, which is the chemical potential of pure I at the temperature and pressure equal to 1, I do not care what it is, it will cancel on both sides. So I will simply write the equations down and cancel it. So to do this, all I do is to take at any temperature T and let us say Tp, I write mu I liquid pure, should write the pure and superscript. This is what I want. I know from thermodynamics that this is equal to Vi. So I integrate this between this point where I can make a connection with the gas. Along that temperature, this is the saturation pressure. So I integrate this, I get mu I liquid pure Tp minus mu I liquid pure at T and P saturation is equal to integral Vi liquid dP from P saturation to P. But this is the same as mu I vapor pure and T P saturation, because the pure substance, in the pure substance at this saturation pressure and temperature, the vapor and liquid are at equilibrium, because this is given in terms, this is simply mu I 0 of T plus RT ln Pi saturation Phi saturation. This is referring back to the way I treated the yes, please. Once I have got mu I 0 on both sides of the equation, I can cancel it off, I do not have to worry what it is. I do not even care if it goes to minus infinity, because it is the identical quantity on both sides. So to complete the picture, let me go ahead and do solvent solute mixtures. For the solvent the model is the same, mu I is mu I pure liquid T P this is a complete specification because gamma I will go to 1 as Xi goes to 1. For solute mixtures I still have log Xi as an ideal solution and simply write mu I reference but for the solute the physical state that I can realize is between Xi equal to 0 and Xi equal to saturation value. If it is carbon dioxide dissolved in water, the saturation value at room temperature and normal pressure would be something like 10 to the power minus 2 mole fraction. Whatever the value, so Xi can vary, Xi is physically realizable or the physically realizable range of Xi. Is 0 to Xi saturation, whatever the solubility limit is. Now there are two constants here, one is this mu I reference and this gamma I which is a function of composition. I had only one unknown to begin with, so I must be able to specify one number uniquely. So I will have to choose an Xi reference at which I choose gamma I to be 1. In the case of pure substances I could go all the way to mole fraction 1, I could use the pure substance as a reference. So here I will simply say since Xi is going to 0 is realizable, I set gamma I equal to 1. You will have this conceptual difficulty that as gamma I goes to 1, Xi goes to 0, you get log of 0, so you get minus infinity there. But we will not worry about it. What I am going to do in thermodynamics, we always cheat you on this. Actually it is very valid, it is not the thing. What you do is get an animal that diverges, but the same animal on both sides of the equation, then you can cancel it. So that is one way of doing it. The other thing, simple way is, although this quantity, this is an expression as a function of Xi, so I can divide this by T and differentiate with respect to Xi, differentiate with respect to T or P. If I divide by T and differentiate with respect to T, I will get a quantity here which represents minus enthalpy of I bar partial molar enthalpy by T squared. On this side I will get some reference enthalpy. This term will vanish because I am differentiating with respect to temperature. So if I do that, if this will vanish in the limit as Xi goes to 0, if I go to very dilute solutions. So what I will do is, although I do not know this animal, I will know its derivative with respect to T or its derivative with respect to P, and I will show you in treating phase equilibrium I do not need to know mu I reference, I only need to know its derivatives.